Alright guys, today we're going to be looking at section 7.4. The video is going to be broken up into two different pieces, so this first video is only going to cover the first part of the notes, and the second video will cover the second part of the notes. So today we're going to be talking about quadratic regression and exponential growth and power rules, and let's see what else. Yeah, I think that's about it. So that's what we're going to be covering today. So we're going to start with just reminding ourselves how we did line of best fit, and that was on our last lesson. So line of best fit, or maybe it was the lesson before last. It's all starting to run together for me. So when you have a bunch of ordered pairs, you would go to Stat, Edit, then we would type in ordered pairs, in the chart. Remember, our chart had to be like L1, L2. Okay, and that's how we typed them in. And then once we had all of our ordered pairs typed in, we would go to Stat, over to Calculate, Option 4, which was linear regression, and we would scroll down to the Calculate, make sure that was highlighted, and then we would hit Enter. Okay, and if we did that with this set of ordered pairs, it gives us this first equation right here. Okay, because this line tends to be close to a straight line, you might want to use the line of best fit. However, if you look closely, you'll see a slight upward curving. So you may decide to find the parabola of best fit. So that's the quadratic regression line. Okay, so when it says parabola of best fit, that is also known as the quadratic regression. So this is the quadratic regression. Okay, and the way we do that is the same way. We do Stat, Edit, type in ordered pairs in chart. Then we go to Stat, over to Calculate, and this time we're going to choose option 5. Then we'll go down to Calculate. So the only difference is this step. Okay, so if it doesn't look like a straight line, then you'd use the quadratic regression if it looks like it has a curve. So when you do that, so when you type it in, once you have your numbers in the chart, it's easy. You could just go back and hit Stat, Calculate, option 5. And this is the equation that it would give you. Okay. Now, so if we look at the points for this one, for figure 716, I want you to type in the ordered pairs listed, these ordered pairs, okay? These ordered pairs right here that are listed. And then I want you to tell me the linear or the line of best fit and the quadratic or the parabola best fit. Okay, so here we're going to do the line of best fit. So go ahead and type in the ordered pairs. And then take turns finding both equations. Okay? All right. Pause it and go ahead and do that. All right. Now, hopefully, for your line of best fit, you got 1166.187x minus 25292.375. That's your line of best fit. Then your parabola of best fit, if you did option 5, you should have gotten 4, 4, 3, 2, 9, 8 x squared minus 1936.899 x plus 28272.8. Okay, and those would be your equations. And then you could predict for any year, because this was balance in the bank account and the line of parabola best fit. So this could be the years, 30, 35, and 40. So you could predict for year 41. You could predict for year 50. You could do it with your line of best fit, but because this is a curved line, this would be the better equation to use to get a more accurate number. Okay. Now, as time increases, the points represented in the amounts in the banking account are further and farther from both the line and the parabola best fit. And if you look back on this sheet, this was your line of best fit. This is your parabola best fit. Okay, so the further you go, the further away from those you go. So this equation wasn't good. Either one of those wasn't the best way to describe it. So the equation describing these data is neither linear nor quadratic. Okay, so the type of equation we would use is an exponential equation. And this is the equation you use, but the more common formula that we use is y equals a, then in parentheses, 1 plus r raised to the t. Okay? Now, if you use the original piece, a is your original amount. B is 1 plus the growth rate. That's why I like to use this formula, because you don't have to remember that it's 1 plus. And x equals time. But if you use this formula, which I like better, your A is your original amount. Your R is the growth rate. and your t is your time. All right, so let's look at this first problem. According to the U.S. Bureau of the Census in 2011, the U.S. population was approximately 307 million, with an annual growth rate of 0.7%. If this growth rate continues at that rate until 2053, what will the population be? So let's look and see what they gave me. Okay, so they told me that my original amount is 307. They told me that my growth rate is 0.7%, which if I put that in decimal form is 0.007. Now, we're trying to calculate how much time has passed. So we're trying to get to 2053, and we started at 2011. That is 42 years. So, y equals a1 plus r to the t. So y equals 307, open parentheses, 1 plus 0.007 to the 42nd power. So that's going to be 307 times 1.00742 to the 42nd power. Now, I'm going to make a note here. Type all in at once. So what you're going to type in is 307, open parentheses, 1.007, then the little caret button, which is the little rooftop button, to the 42nd power. And that gives me an answer of 411.51 million. That's what the population would be, according to the rate at which it's growing. Okay. Now, when using a mathematical model as an example 1, it's also important to consider the appropriateness of the model. For example, you should ask whether it's reasonable to assume that the growth rate in the United States will stay at 0.7% for 42 years. No, because we'll have all kinds of things that will either make the growth rate expand or be larger, or will make the growth rate slow down. Okay. Often in media, researchers make dire predictions based on the mathematical models such as things like population growth, global warming, and bankruptcy of the Social Security system. Okay, the predictions may or may not be valid depending on the assumptions made by the researcher. As an educated person, you should have an understanding of what mathematical model can tell us and what it cannot. If the assumptions underlying a model are not sound, then its predictions are worthless, because we can make numbers say what we want them to say, but you have to understand if your model is reasonable. In predicting future bank balances, population, or other similar quantities that are growing exponentially, we often want to know, how long will it take for this quantity to double? Before we can answer this question, we need another tool. The log function has an important property that will help us solve equations of the form a equals b to the x. For example, we may want to find the value of x such that 5 equals 3 to the x. Though it may seem strange to you, it is possible to find the number, although not the integer. So there's not a number that we can go 3 to the what power gives me 5. Okay, that's not going to be reasonable. Okay? In order to do that, we need to follow the property of the log function. Okay? And what this is called, if you remember back to Math 3, this is the power rule of logs, which says, and it says you can bring the exponent down and out front. So remember what we said with powers. What do we do with powers in exponents? We multiply them. So what we can do is take this power, because logs are just like cousins of exponents. So we can bring this power down and it becomes a multiplication fact. Okay? So I'm going to highlight this right here. All right. So we're going to do example 2 and 3, and then we will be done for today. In 2011, India's population was 1.2 billion. Okay, so that was our original population. Okay, with an annual growth rate of this. So this is my R. Okay, assuming that the growth rate will remain the same, in what year will India's population double? So, they are telling me that the population 1.2 will double. So that will be 2.4. So they're telling me what y is going to be. Okay, they're telling me what y is. We're going to have to solve for t. Okay, so if we look at the equation, y equals a times 1 plus r to the t power, and we plug in what we know. We know 2.4 equals 1.2, 1 plus, and remember this is going to be 0.0158, 0.0158 to the t. Okay, so this is really 2.4 equals 1.2 times 1.0158 to the t power. Now, we know if we're trying to solve for t that we can move the 1.2 over by division. So that's going to leave me with 2 equals 1.0158 to the t power. Now, this is when we're going to get stuck. Okay, I'm going to write a note up here at the top. When solving for an exponent, turn it into a log problem. Okay, so I'm going to put a little star here. So what we're going to do is we're going to put logs on each side. We're going to come up here. We're going to put logs on each side. And then we remember our power rule for logs. If we have an exponent and it's a log problem, remember we're allowed to bring this t out front. So this is going to be log 2 equals t times log of 1.0158. Okay, now our goal is, and I'm going to write the note here that says power rule. Okay, now our goal is to get t by itself. This stuff is being multiplied, so we're going to move it over here, and what we're going to do is divide it. So we'll take log of 2 and divide it by log of 1.0158. So we're going to type that into our calculator. Now our log button is located beside of our 7. Because there's stuff on top and on bottom, we're going to put it in parentheses. Log of 2, and every time you press the log button, it's going to open a parenthesis. So that's our top, divided by, and I know that it might not do anything having this extra set of parentheses, but it's better to have too many than not enough, as long as you close them all. Okay, then you're going to hit enter. Okay, so I'm going to make sure that I have parentheses around this so you know what it looks like on your calculator. And that gives me 44.22. Okay, so 44.22 years, which means that's going to be into the 45th year. So if we're in 2011 and we add 45 years, that's going to be in the year 2056. Okay, let's do one more like that. The price of a product increases exponentially due to inflation. Suppose that in 2006, a pair of Ugg boots cost $130. Okay, and in 2011, due to inflation, same pair cost $150. So that's our Y. Okay, now we can figure out our time. Okay, our time is going to be 2011 minus 2006, which is 5. Now remember, our formula is Y equals A 1 plus R to the T. So we know that 150 is our Y, 130 is our A, then we have 1 plus R to the 5th power. Okay, so the first thing I'm going to do is I'm going to divide 150 by 130. And that gives me 1.154. Now, this 5 is holding this hostage. So to get rid of a 5th power, I'm going to take the 5th root. Okay? So to do that, you're going to go over to math and you're going to choose option 5. Now, if you have an old calculator, you're going to have to hit 5 before you go to math option 5 to tell it what root you're taking. But we have the blinky box in the new calculator. So 1.154. Again, if you don't have a newer calculator that has blinky boxes, you'll hit 5, then math option 5. Okay? I think it was option 5. Yeah, option 5. So now that's going to give us 1.029 equals 1 plus R. Now we're trying to find R, remember, so we're going to subtract the 1. So it's 0.029 is your R. Okay, so our exponential model is y equals 130, 1 plus 0.029 to the t power. Use the model in Part A to estimate this cost of a pair of boots in 2020. So when we started this, it was 2006. So 2020 minus 2006 is 14 years. So we use our formula here, 130, 1 plus 0.029 to the 14th power. So we're going to do 130, 1.029 to the 14th power. And you type all that in at one time, and you get $193.98. Okay? All right? And if you need to listen to that again or look through it again, take your time. And if you have any questions, please let me know. Thanks. Have a good day.